Hello, thanks for watching. Made a video here that's going to focus on a different kind of collision that other videos that I've made have focused on, and that is a two-dimensional kind of collision. So before we had one dimensions, which is, for example, in a physics lab situation, a lot of classrooms have the tracks on which you run the carts. But it's a little bit like a train on a track. You can't turn different directions without turning the track, so those are what we call one-dimensional. So we can go forwards or backwards, we could go left or right, but we can't go in two dimensions at the same time, like north and south. But in a two-dimensional collision, we're going to have that ability. So I'm going to show you how, although the principle of the conservation of momentum is the same, the problem-solving process looks a little bit different. So let's just draw an example out of what a two-dimensional collision might look like. And I'm going to focus on an inelastic collision in this video, and I'll do a different one for the elastic kind of collision. So suppose we've got a 4-kilogram object, and I'm just going to make this a pictorial model here, and it's moving at, let's say, 10 meters per second rightward, or maybe we'll call it eastward. You can't tell from the picture which way that is. And going to collide with a 5-kilogram object that's moving at, let's say, 6 meters per second. And it's moving what we'll draw downward or southward. So I haven't drawn them in just the right spot to be able to collide, but imagine these things collide and stick together. So that's why we call it inelastic. So what's this going to look like? Well, we're going to have a big glob here of 9 kilograms, and I hope you can get an idea of which way it's going to be moving just in general. We'll find out specifically in a moment, but if we've got some rightward and some downward colliding together, we have to end up with some rightward and some downward. It's just that it's just one object moving, so they're not separate here. So we would be asked to find what the final velocity of that combination is. That's going to be our problem-solving procedure. So in my previous videos, I showed two different ways of organizing your information. One that I like is called a momentum table, and the other is just an algebraic equation. So I'm going to show you how those look a little different for the two dimensions. And this is where students make mistakes on these. They try to solve them just like the one-dimensional collisions, and that doesn't work because there's no way to account for the direction piece. So in the table format, I'm going to make a table like this, where each object has its own line. So the 4-kilogram object has a line, the 5-kilogram object has a line, and then we have a line here for the total. And then what we do is we compare the before momentum with the after momentum. Often those are referred to as initial and final. So this cannot be just a number in each of these. This has to be a vector that describes both the magnitude, that's the number in the unit, plus the direction piece. So I'm actually going to draw an arrow into each of these boxes. So we have a total of 10 meters per second. That's 40 units of momentum. I'm not going to write the units in because it gets a little bit tight in these. But I'm just going to draw a right arrow with 40 for the 4-kilogram object. And then we have a total of 30 units of momentum. And by the way, I just noticed on this figure I wrote 5 grams. That should be kilograms. I'm not going to make too much of that. I'm not drawing these to scale either. So 30 units of momentum downward. So now you should know how to combine vectors that aren't going along the same line previously in a course. So if you add a 40 rightward to a 30 downward, you need to draw a little diagram for that. And I'll just put it over here. 40 this way, 30 this way. We arrange them head to tail, and then we draw in our resultant vector. This is the sum of those two, which goes from the tail of the first over to the head of the last. And I made the numbers kind of nice so that I could do this in my head. That's a 3, 4, 5 right triangle. So that's 50 units of momentum. And I also, just because when I was younger we didn't have calculators to do this, I tended to memorize these special triangle angles. This is a 37-degree angle that makes. So I'm going to draw that in this way, 50 units of momentum at 37 degrees below rightward. Now we're going to apply the conservation of momentum principle. If that's my momentum before the collision, that also has to be my momentum after the collision. So I'm going to draw an identical vector, 50 units, pointed 37 degrees below rightward. And the only difference now is that momentum is due to this 9-kilogram object moving. So if I want to know what the final velocity is, I can just take the final momentum and divide it by the mass. So I have 50, I'll go ahead and put units in now that I've got some space, kilograms meters per second, divided by 9 kilograms. Kilograms are going to cancel. 50 over 9 is, I believe, about 5.56. And then I would need to describe the direction. Now I like to describe directions counterclockwise from 0, so that would be 360 minus 37, which is 323 degrees. Hopefully I did that math right. So that describes the final velocity. But we got to it through momentum. You can't just use the velocities. There's nothing special about just the 10 or the 6. You must use momentum, and we had to account for the directions. I didn't complete the table here because it's, although we could certainly go back up now and multiply this velocity by 4 and multiply it by 5, and they would each have the same direction for the velocity, but I'm not going to go through because we really don't need that. Now, I told you I'd show you the algebraic form of this. When we do one-dimensional problems, I like to write it out this way. I take the mass of each of my objects and its initial velocity. So that'd be m4 and its initial velocity, plus I'll call it m5 and its initial velocity. And we say that has to equal the total at the end. So this is m4 plus m5 with inelastic. I like to combine those masses. And then the one common final velocity that they share. But what people like to do here is just forget about all the directional stuff. So sometimes you'll see that we denote that these are vectors, not just to be formal, but just to remind you that you have to account for the direction part. So you must do this with a figure. You have to draw, like I drew up here, a rightward vector that's 40 and a downward vector that's 30. And then you have, the vector that we had up here, the 50, going like that. So it's really not a different way of finding the answer. It's just maybe a different way of organizing your information. So that's a great way to do the inelastic collisions. And even if you have a problem where perhaps you know what it's doing after the collision and you were asked for one of these pieces, it's just the same kind of information but solved in the other direction. So I'll let you maybe take a look at those on your own. I will make another video that'll show a two-dimensional collision that's elastic in nature. So if you have something like that, need to see maybe how to approach that, you can check out that other video. That's going to do it for now. Thanks for watching.